Hi everyone, welcome to AI Crack channel. This is Akash Gangwar and today we'll be studying definite integrals lecture 1. In this lecture we'll be talking about basics of definite integrals and few properties. Okay. So let's begin our lecture with the understanding definite integrals with area. In case of indefinite integrals, what we primarily did was reverse of differentiation, right? But in this case we have to understand definite integrals with the help of area. So let's say we have a curve like this. This function is fx. Okay. This point is A, this point is B. Okay. And since the function is fx, this point would be f of a and this point would be f of b, right? Now let's say we have to estimate this area. And this is not a standard shape because this is curved over here, right? It's not a straight line, it's a curve. So that's why it's not a standard shape. So we have to estimate the area. So the best possible way is to try to find out this area with the help of rectangle. But in this case, what's happening? We're missing out on this part. So it's not having a good accuracy, right? So let's do one thing. Let's try to divide this entire region into two parts, two equal parts, basically parts of having equal width. Okay. Now in that case, we are able to form two rectangles, right? In this case, we can find out this area, we can find out this area. We are missing out on this one and this one. But we can see that our accuracy has improved, right? Now let's say we are dividing this area into four parts of equal width, right? In that case, what's happening? We can see that we're able to find out these areas and we are missing out on these ones, smaller ones. Again, we can see that our accuracy has improved. So let's do one thing. Let's try to divide this area into very small, very thin strips, right? Very thin, infinitesimally thin strips. Okay. So let's say this is a very thin strip. Okay. And this length is dx, which is very small, very, very small, infinitesimally small. It is at a distance of x from here. Okay. X from origin. Okay. Now, at this particular point, this function value would be f of x, right? And function value is nothing but this height only, right? So for this particular rectangle, area would be delta equals to fx into dx. Dx is the width and fx is the length, right? Now, if we do the summation over here, summation fx dx, we'll be able to find out all these strips over here with basically area of all the strips, and we are summing them up. So that would give us the entire area for this particular region, right? Now, when we apply limit over here, basically we are making dx so small that it is approaching 0. In that case, we can write this as integral a to b fx dx, right? So that is the significance of integral fx dx from a to b. Basically, it's the area under the curve. Okay. Now, one important thing over here, whenever the curve is above x-axis, in that case, area would come out as positive. And whenever the curve is below x-axis, in that case, area would come out as negative. But mind that we are going from here to here. Okay. So in case we are going from left to right and function is above x-axis, in that case, area would come out as positive. And when we are going from here to here, basically from left to right, and the function is below x-axis, in that case, area would come out as negative, right? Don't forget this part. We are going from A to B. We are going from left to right. Okay. And now let's talk about basics of definite integrals and changing of limits. Okay. So let fx be a continuous function. This is the most important keyword over here. Let fx be a continuous function defined on A to B, right? This should not be forgotten. It should be a continuous function. This should be a continuous function defined from A to B. Okay. So whenever this is happening, we can write this as fb minus fa. So that basically means if integral fx dx equals to capital Fx plus c, right? In that case, integral a to b fx dx would be fb minus f of a. Okay, this you have to remember. But the most important thing over here is the function should be continuous between a to b, right? Only in that case you'll be able to use this particular formula. Okay. And now what about changing of limits? Let's say we have integral 0 to pi by 2 cos x ln sin x dx, right? Now we can see that we have a composite function over here and sin x is the argument. We have cos x dx, right? So that gives us the hint that we have to use sin x equals to t as a substitution, right? So if we differentiate this one, we'll be getting cos x dx equals to dt, right? Now this integral becomes this cos x dx is dt, ln sin x is ln t dt. Okay. Now what about limits? So when x equals to 0, this t would become 0 only because sine 0 is 0 only. When x equals to pi by 2, sine pi by 2 is 1, so t equals to 1. So this is how you have to change your limits. And now let's solve this example. We have integral 3 to 8 sine of under root x plus 1 divided by under root x plus 1 dx, right? Now we can see that this is a composite function and under root x plus 1 is the argument of this composite function, right? And we also have dx upon under root x plus 1. So considering everything, the obvious substitution over here is under root x plus 1 equals to t, right? So if you differentiate this one, you'll be getting 1 upon 2 under root x plus 1 into 1 dx equals to dt, right? So this gives us dx upon under root x plus 1 equals to 2 dt, right? Simple. Now this integral becomes sine t and this becomes dt, right? Now what about limits? So when x equals to 3, this t becomes 2. When x equals to 8, this t becomes 3, right? So this is the final integral. Now integral sin t would be minus cos t going from 2 to 3, right? So this actually becomes minus times cos 3 minus cos 2. This should be our answer. Okay. And now let's solve this example. We have integral 0 to 1 x times ln of 1 plus 2x dx. Now we can see that this is a log function and this is an algebraic function, right? So we have to use by parts because we cannot use any kind of substitution over here, right? So if we write down our isolate 1, we can see that algebraic functions are coming after log functions, right? So basically log functions are tougher to integrate as compared to algebraic functions, right? So this function would be marked as first function and this is second function, okay? So this integral becomes first function into integral of second, that is x square by 2, 0 to 1, minus integral of derivative of 1, that is 1 upon 1 plus 2x multiplied by 2, into integral of second, that is x square by 2 dx, right? So this 2 gets cancelled out. Now I can see that this is very standard, no? So if you do this one, if you solve this one, we'll be getting ln of 1 plus 2 into 1 dot 1 by 2 minus ln of 1 plus 2 into 0 multiplied by 0 by 2. So this is 0 only. So ultimately what we have got ln 3 by 2. So this portion is sorted, right? So this is nothing but ln 3 by 2. Now if we talk about this one, let's say this is I. Okay. So what we can do, we can multiply divide by 4 over here. So we have got 1 upon 4 integral 4x square dx divided by 1 plus 2x. Why I did that? Because after this I'll be doing plus 1 and minus 1. And this portion 4x square minus 1, that would generate 1 plus 2x and 1 minus 2x in the numerator, right? So that would help us cancelling out this denominator. Okay. So this actually becomes 1 by 4 integral 0 to 1. This is 2x plus 1, 2x minus 1, basically clubbing 4x square minus 1 divided by 1 plus 2x dx plus 1 by 4 integral 0 to 1 dx upon 1 plus 2x, basically remaining 1 upon 1 plus 2x, right? Now this is again pretty standard. This is nothing but 1 upon 2 ln of 1 plus 2x, right? You can again put down the limits. In this case, this and this gets cancelled out. What we have got 1 upon 4 integral 0 to 1 2x minus 1 dx. This is again pretty standard. Yeah, you can calculate this one and this one, right? And this was ln 3 by 2. Okay. So this question was pretty calculative, and similar kind of calculative question was there in PGDBA 2023, right? So that also involved by parts, and that was just pure calculation, no trick, just pure calculation, right? So you have to be patient over there to solve these kind of questions, and you'll get the answer. Okay. Now let's talk about properties of different integrals. So the property one is integral a to b fx dx equals to integral a to b ft dt. That's very simple, no? Let's say we use the substitution as x equals to t. So dx equals to dt. What about the limits? If x equals to a, t equals to a. If x equals to b, t equals to b, right? So this integral becomes a to b ft dt. Very simple. That's very simple, right? You don't even need the proof for this one. Now let's talk about second property. We have integral a to b fx dx equals to integral minus b to a fx dx, right? Now what's happening over here? Let's say integral fx dx equals to capital fx plus c, right? In that case, what we can write? We can write integral fx dx a to b as f of b minus f of a. Basic property, no? Right? Now, let's say we are talking about this one. In this case, what we are doing? Minus of integral b to a f of x dx, right? So this actually becomes minus times f of a minus f of b, right? So this actually becomes fb minus fa. So this is same as this one, right? Hence proved. And now if we talk about property 3, we have integral a to b fx dx equals to integral a to c fx dx plus integral c to b fx dx. So integral is broken at points of discontinuity or at points where function definition is changing, right? So what do we mean by that? So if you remember, we talked about a to b integral fx dx equals to capital F of b minus capital F of a, right? We talked about this. This is only true when this function is defined between a to b and also continues between a and b, right? So this formula is only true when this function small fx is defined between a to b and also continuous between a and b, right? Now let's try to demonstrate with the help of a graph. Okay, so let's say we have a function which is discontinuous at a particular point. So this function looks like this. Okay, so this function definition is x square plus 1 from 0 to 1 over here, and from 1 to infinity the function is x cube plus 2. Okay, let's say we have defined the function like this, and we have a discontinuity at x equals to 1. Okay, now what's happening over here? When we're writing this formula, integral a to b fx dx equals to capital F of b minus capital F of a. When we're writing this formula, we are saying that we have a unique integral for this entire function, which is true, right? Because this function is continuous, so that's why we have a unique integral, that is fx plus c, for this entire integral, right? So that's why we are able to write this particular formula. But over here, when we have a discontinuity, basically we have created two functions. In short, what we have done is, when we have a discontinuity, we have created two functions, right? We are defining them as one function. When we are defining, okay, fx equals to, we are defining them as one function based on piecewise function properties. But in reality, from here to here, from 0 to 1, it's a separate function. From 1 to infinity, it's a separate function. So it cannot have a single value, capital Fx, satisfying this integral, right? So that's why we have to break down that function at the point of discontinuity. Now this function is continuous over here, and this function is continuous over here, and we can use this separate integral and separate integral. Okay, so that's how we have to do this. Okay, and now let's solve this example. We have integral 0 to 3 g f x dx. Now we know that GIF function is discontinuous at integers. So for 0 to 3, GIF function would be defined as 0, 1, and 2. So for 0, range would be x less than 1, bigger than equals to 0. For 1, range would be x less than 2, bigger than equals to 1. And for this one, it would be x less than 3, bigger than equals to 2, right? Now we have defined this function to three parts, basically three continuous parts. In this range, this is continuous. In this range, this is continuous. And in this range, this is continuous, because it's a constant function. Okay, so we can break down this integral to three parts. The first part would be 0 to 1, and we have 0 dx because function is 0 over here, right? Second portion would be 1 to 2, and this would be 1 dx, right? And third portion would be 2 to 3, and we have 2 dx. Okay, so now you can solve this integral. It's very simple. Okay, and now let's solve this example. We have integral 0 to pi under root 1 plus cos 2x by 2 dx, right? Now whenever you see 1 plus cos 2x, the first thing that should trigger in your mind is 2 cos square x, right? So this integral becomes 0 to pi under root 2 cos square x by 2 dx. So this 2 and 2 gets cancelled out. What we have got under root cos square x, that is nothing but mod cos x, right? So we have got 0 to pi mod cos x dx. Now we know that mod cos x is changing its definition at pi by 2. So we have mod cos x equals to cos x and minus cos x. This portion when x is less than equals to pi by 2 and bigger than equals to 0, right? And this portion when x is less than equals to pi and bigger than pi by 2. Okay, so we have broken down this function into two parts. So basically definition is changing for this particular function, so integral should change. So this would become 0 to pi by 2 cos x dx minus integral pi by 2 to pi cos x dx. Now you have to calculate this integral. Very simple. Okay, and now let's solve this example. We have integral minus pi by 2 to pi by 2 under root cos x minus cos cube x dx, right? Now this integral can be written as minus pi by 2 to pi by 2 integral under root. Let's take cos x is common. We've got 1 minus cos square x dx. Now 1 minus cos square x is nothing but sine square x. This becomes sine square x, right? Now this can be written as minus pi by 2 to pi by 2 integral under root cos x multiplied by mod sin x dx. Why mod sin x? Because under root sine square x is mod sin x. Okay. Now we can see that the definition of this function is changing because of mod sin x. Sin x is negative from minus pi by 2 to 0 and sin x is positive from 0 to pi by 2. So that's why we have to break down this function into two parts because of change in definition. So you can keep that as homework. That's same as last example. Okay. So today's lecture was till here only, and we'll talk about property 4, 5 and 6 in the next lecture. So let's meet in the next lecture. Thanks for watching.